Uh, if f is differentiable, then f is continuous. Okay. This statement, roughly speaking, differentiability is stronger than continuity. Means differentiable at some point is a sufficient condition for continuous at some point. Or differentiability implies continuity. Just now I missed this lowercase a at a. Let's find the derivative of a given function. Example 2. Find a formula for f prime of x and illustrate this formula by comparing the graphs of f and f prime. In order to find the derivative of f, we can use f of x plus h minus f of x over h, then take limit. If at some a you can use another equivalent expression to denote the difference quotient and find its limit. F of x is x cubed, x plus h cubed minus x plus h. F of x, x cubed minus x. This one by binomial theorem. Here, x cubed and x cubed, these two numbers are cancelled. X and x are also cancelled. And the rest terms all as the factor h. Now this is a polynomial of h, or polynomial in the variable h. H approaches 0, we evaluate this limit by direct substitution. So this is the formula this is a formula of f prime of x. Now compare two graphs. Y equals x cubed. Y equals minus x. So, y equals x cubed minus x should be by superposition at x. The value is the sum of these two numbers. So I mean, superposition, okay? So we obtain this one. This is the graph of this function. Okay. Y equals x cubed minus x. Whose derivative is the slope function of the original of this one. The slope here is minus 1. Slope here is 0. Slope here is also 0. Okay, from minus to 0, then 0 to plus. Minus to 0, then 0 to plus. Positive to 0 to minus. Positive to 0 to minus. So this is y prime. 3x squared minus 1. See? X squared, the parabola. 3 minus 1. Okay? Stop here. Minus 1. Stop here. Horizontal. Slope here. So at x2, 0. In fact, slope here, 0. Slope function. Okay. Derivative is the slope of the curve. The slope. Motivation 1. Motivation 2 is velocity. Okay. So f prime of 0 equals minus 1 means the slope of the tangent to this curve at origin is minus 1. minus 1. So this one, f prime of 0 is minus 1. Minus 1. Slope function, okay, slope, got it? Understand? Good. So, this limit stands for the slope of the function at x. For example, at 0, the slope is minus 1. At somewhere the slope of tangent is 0. Where? By solving this one equals 0, you can find x equals plus or minus 1 over square root of 3. So, slope, just slope. Therefore, if we have no additional, no further tools to find the derivative, the only way to find the slope or derivative is by definition. Find the limit of the difference quotient. The following example is to find the derivative of the square root function. Of course, domain of the derivative of f. Since this function is defined only for non-negative numbers, at the origin we cannot find two-sided limit of the difference quotient, then we consider a positive number x. We have done many exercises before. So for finding this limit, we multiply both square root of x plus h minus square root of x on top and the bottom. X and X are cancelled. H and H are also cancelled. Since the square root function is continuous on any positive number, and x plus h is a polynomial in h. Therefore, the limit of this one can be evaluated by direct substitution. And this one is positive, so everything is legal. Therefore, we have therefore the domain of the derivative of f is this open interval. In other words, f is differentiable on this open interval, on this infinite open interval. Okay? Since for a given function whose derivative is also a function of the variable x, of course, on its domain, so we can find the derivative of f. So the original one may be called the first order derivative, and the derivative of f may be called the second order derivative, and so on, or simply first derivative, second derivative, and the order omitted. And because this is so useful in many areas, there is another very famous notation to express the derivatives. DD notation. Suppose we have a function, use this functional notation, y equals f of x. X is the independent variable, y is the dependent variable, and f is the name of the function, f. F prime of x is the derivative of f at the number x. If we emphasize the dependent variable, we can use y prime. And we may use dy dx. dy dx. This notation was introduced by Leibniz, the German mathematician Leibniz. He has invented the calculus independently with Newton. Dy dx, because we know f prime x equals delta y over delta x. This one is called instantaneous rate of change of y with respect to x. if we emphasize the function f, we may write df dx. Or even we emphasize this function whose variable is x. If we treat this as some kind of function, before the function f maps number to number. Now this one seems a new kind of function or superfunction. Maps f to its derivative. This one so we may treat d dx as an operator. Operator means some kind of function whose domain is functions, a set of functions, whose codomain is also a set of functions, maps function to function. Original, before the function means maps some number to number, but now we may treat this one or prime or ddx as an operator. Operator means some kind of function. We use operator to emphasize the domain of this function is a set of some functions. Okay. Or briefly, d or anyway. So mainly there are three kinds of expression. One is prime notation. The second one is D notation. And the third one is use capital D. Capital D. They are all the same. They have the same meaning, the derivative of the function f. Okay, derivative. So other notations for derivative besides prime notation, we have this dd. Notation. And this one was introduced by Leibniz, okay, dd notation. In dd notation, we may treat ddx as an operator or differentiation operator. Operator means it is a kind of function and whose domain is a set of functions. Codomain is also a set of functions. Well, so we have this notation. And before, when we used the prime notation, the derivative of the function f as some number a now becomes to y prime x equals a, or dy dx at x equals a, and so on. Anyway, by inspection, immediately you realize the meaning of that notation. I think so. if you want to find the value of the derivative at some number, use prime notation or dB notation. You can restrict or add a. Higher derivatives or higher order derivatives. Order again omitted. Well, f prime is the derivative of the function f. If we use double prime, this means the prime of f prime and x. Okay, double prime. The second order derivative. This is the prime notation. If we use dB notation, we have d, dx, dy, dx. And this one will be denoted by d squared or yc to d. And dx, we use dx squared. We don't need a lousy parenthesis. Okay. If we use d notation, or for example f of x, anyway, triple prime means the third order derivative of the function f, which is the derivative of the second derivative. If we use dB notation, will be so if we have 3d, d cubed y dx cubed. In capital D differential operator, d cubed f, or f of x anyway. But more than the third order derivative, we will use in this textbook, we use an exponent index here, the nth derivative. Or anyway. So this is the first order derivative. The second order, third order, the nth order derivative of the function f. Higher derivatives. In physics, suppose S denotes the position.